Good morning, everyone. So today we are going to discuss the concept density of states. Uh, before begin with the density of states, so we need to understand what is the quantum mechanical background for the calculation of these density of states. So, in order to calculate the density of states, we have to consider the free electron dynamics in case of metals. So in metals, we have a free electrons. So the potential energy of these electrons are zero in case of metals. Because in metals, the atoms are always stuck, whereas the electrons are free. They are not constrained by the atoms, so they are free. So that the potential energy is always zero. So in order to understand the dynamics of these electrons, we have to use the Schrodinger wave equation. Using the Schrodinger wave equation, we have to evaluate the quantization of energy levels. So the quantization of energy levels will give the complete idea of calculation of the density of states. So let us begin with the idea concept. So we have to consider a one-dimensional potential well. It is like this, and we have a boundary conditions 0 to a. So you have an infinite potential well. So the potential is infinite here, but electron is trapped here. So this electron is moving back and forth and interacting with the walls of these well. So the potential energy is zero within this wall. Outside the potential is infinite. Of course, the potential is infinite. So what will be the wave function? The wave function is a definite and single valued within this potential. Outside the wave function is zero. So you cannot predict the existence of particle outside this well. And outside this well, you have an infinite. You don't have a boundary conditions in order to identify the location of the particle. So we have a boundary conditions for this v of x, which is equal to 0, where it is 0 less than or equal to x less than or equal to a. So this is the boundary conditions. So this is for infinite, potential is infinite, otherwise these are the boundary conditions. Now we need to take the Schrodinger wave equation, that is one dimensional Schrodinger wave equation, t square psi by dx square plus 8 pi square m divided by h square e minus v into psi, which is equal to 0. This is equation 1. So now we have the this Schrodinger wave equation pull all the information of potential, energy, the wave function, and the uh, whether the particle is moving in one dimension or it is in a three dimension, so on. All this information you will get in a single equation. So that's why Schrodinger wave equation is an equation of motion for the fundamental atomic or fundamental particles. So now we have to solve this differential equation. So d square psi by dx square plus 8 pi square m h square. Here the potential energy is 0, so that this will be simply reduces to this form. So that is d square psi by dx square plus 8 pi square m h square e, which is equal to 0. So this is a second order linear differential equation. So we have to solve this differential equation in order to find out the solution of this wave function. So now here I considered the some parameter k square is equal to this 8 pi square m h square e, which is equal to 0. This k is the constant. Later we will deal with the importance of this k square. So then the equation 2 becomes d square psi by dx square plus k square psi, which is equal to 0. This is of the equation 3. Now this is the second order linear differential equation. So if you solve this differential equation, you will get the solution. That is, solution is psi of x a sin kx plus b cos kx. So this is a solution. And here I make a simple calculations. So if you have this equation 8 pi square m divided by h square e, which is equal to k square. Here also you have the wave function psi. Here also psi. Okay. So now if you differentiate this d square psi by dx square, then you will get the k square into a sin kx plus b cos kx. So this is a minus kx square, because you can differentiate this square, d square psi by dx. You will get the same of this term, which is equal to d square psi by dx square minus k square. This is of the form psi of x. Again you can do this d square psi by dx square. You can bring this k square in the left hand side plus k square psi of x. Of course you will get the same expression of this. Same expression. So let us apply the boundary condition. Apply the boundary condition. Boundary conditions. So for boundary conditions, you have two boundary conditions. At edge, at x is equal to 0, at x is equal to a. You have two boundary conditions. So let us consider apply the boundary conditions. At x is equal to 0, at x is equal to 0, the potential energy at the boundary conditions is, the wave function is 0. So then this equation becomes, at x is equal to 0, you can apply the boundary conditions to this equation. The wave function at x is equal to 0, psi is of course 0, because at the edge you cannot identify or locate the particle existence. So psi is equal to 0, a sin k of 0 plus b cos k of 0. Of course a sin 0 is 0 plus b cos 0 is 1, it is simply b. Therefore b is equal to 0. Then apply the second boundary conditions, that is at x is equal to a. You have two boundary conditions, at x is equal to 0 and at x is equal to a. Now at x is equal to a, so then again the boundary condition psi also 0. At the edges always the potential is infinite, so that a wave function is also 0. So then again apply this boundary condition to this equation, above this equation. It becomes 0. You have a sin ka plus b cos ka. But we know that a sin ka, as it is we are writing, but b is 0. You substitute this b over here, it will become 0. Therefore you have a sin ka, which is equal to 0. But a is not equal to 0 because it is constant. Then sin ka is equal to 0. We got this. Now we know that you can take any value of sin pi, sin 2 pi, sin 3 pi, so on sin n pi. which is equal to 0. But we know that the sine pi, using the trigonometric functions, sine pi is 0, sine 2 pi is 0, sine 3 pi is 0, so on, sine n pi is also 0. Therefore, here you can take here sine a is not equal to 0, so that sine ka is equal to 0. Sine ka is equal to 0. In this 0 place, I put sine n pi, because sine n pi is also 0. So sine ka is equal to sine n pi. So then sine gets cancelled. Then you will get the k value. So that is, if sine n pi sine ka, so therefore sine, it is simply ka, which is equal to n pi. Then we want the value of k, which is equal to n pi by a. So this is the value got. So therefore, we know that we know that we know that you have a equation k square is equal to 8 pi square m e by h square. We know that this k is, substitute n square pi square divided by a square, which is equal to 8 pi square m e by h square. So cancel out this pi square. So this just cross multiply, you will get I bring this e is here in the left hand side. So this n square h square divided by 8m a square. So this is the well known equation, that is the eigen energy equation evaluated using the Schrodinger wave equation. So this is the eigen energy values, or simply it is energy equation or quantization of energy equation. So this is equation 4, and this is a very physical significance. It has e, you can also write down, it is of the form n square pi square n square pi square h cross square divided by 2ma square. See, if you elaborate this, wherever you have h cross square, you can, h cross is h by 2 pi. So it is h cross square is h square divided by 4 pi square. So 4 into 2, 8. So you will get the same expression. Nothing change. And here, so we can write this is of the form, whereas here this n pi a square, you just carefully observe here, n square pi square by a square, that is k. So we know that the k is equal to n pi by a. So n square pi square by a square is simply a k square, which is equal to n square pi square by a square. So then E is equal to, this is of the form h cross square k square divided by 2m. So what exactly this equation? It is a kinetic energy of an electron. It is simply p square by 2m. That is the kinetic energy. We know that the h cross is h by 2 pi into k is 2 pi by lambda. 2 pi gets cancelled. H cross is h cross k is equal to h by lambda, which is equal to p, that is the momentum. So we have substituted the p square. So h cross square k square is a p square. So that is the kinetic energy of electron. So here, what is this? The relation E is directly proportional to k square. So what is this k? This is the electron wave vector, and it takes the value k is equal to plus or minus n pi by a. So this k is the electron wave vector. It has in plus or minus n pi by a values. For the different values of k, the allowed values of k, the energy will decide. So this is the energy of quantization of energies. So we need to understand, based on this quantum mechanical treatment, we have to understand the density of states. So in the previous section, we have considered the density of states. So what is the density of states? Density of states. So the density of states means that the number of available energy states in the energy range from E to E plus dE divided by the total volume of the system. So that is the density of states. You can write down the mathematical expression. It is N of E into dE, which is equal to F of E Z of E into dE. So here this N of E is the number of occupied states, and F of E is the probability factor. Also we call it as the Fermi factor. Then so this Z of E is the number of available energy states in the energy range from E to E plus dE. So let us clarify with this by writing the flat band diagram. For example, uh, flat diagram. So we need to understand how this work out. See, this Z of E is the number of available states, and F of E is the probability deciding factor or Fermi factor, and this N of E is the number of occupied states. So for example, so here you have a uh, bands. So these are all the set of valence band. According to Pauli exclusion principle, each quantum state is occupied not more than 2 electrons. So all these electrons are occupied up to the Fermi level. Above this Fermi level, you have an available states. So these are the available energy states. So these are available states. We call it as a Z of E. And here, once the temperature is raised, so these electrons are start occupying the higher energy level like this. So if the electron is occupied the higher energy level, some parameter is required to find out the probability. So that is the Fermi factor. So this Fermi factor is the probability deciding factor, so which can determine the probability of occupation of electrons in the available energy states. And Z of E is the total number of available energy states. Okay, so therefore we know that expression N of E, and we are evaluating the energy E to E plus dE. Whole energy we are considering, we are integrating this integral of e to e plus d. In order to get the entire area, we use the integration sign, because the in order to find out the number of available energy states. So this n of e into dE, which is equal to the probability factor for f of e and z of e into dE. So this is the occupied states. So n of e is the occupied states. So it will give the information about how many states is occupied by electron. So therefore this f of e is the probability deciding factor. This z of e is the total available energy states in the range e to e plus dE, so that we get the total, the density of states, that is n of e into dE, which is equal to f of e into z of e. So this is the density of states expression. So how do you calculate this z of v? So this is a simple mathematical equation, but we need to calculate the density of states. I mean the number of available energy states we have to find out. So in order to find out this z of v, we have to construct the Fermi surface or the Fermi sphere. So that is a three-dimensional case we have to consider. For example, we know that E, which is equal to, already we have written h cross square k square divided by 2m, or else you can write down, it is simply, it is of the form n square h square divided by 8 ml square ma square. So this is of the same form. So now E, which is equal to, n is the different quantum states. So n we can write nx square in three dimensional, ny square plus nz square into h square divided by 8ma square. See here, these are the quantum states in three dimensional. So all these are the constant quantity. For any number of positive integer, if you consider any number of positive integer, the energy will be constant or energy will be same. So this is the you can consider this is the radius, this n square, n is the radius of the sphere. So what is the area? Area is constant. So that is, if you can consider the modulus of this nx square, ny square, nz square, it is constant. So that the area of the circle is constant. Same way, based on this, we have to construct the Fermi sphere or Fermi surface. So that is the three-dimensional case. So you have a three-coordinate system. Nx, ny, nz. So this is the Fermi sphere. We have to construct the Fermi, we have to represent the Fermi sphere in three-dimensional representation. Like this. So here so this is nx, ny, and z, and here this is a Fermi surface. Now, so these are the energy range. So this is a radius n. So this n is the decides n is the radius of this sphere, and nx square, ny, z, n square, the modulus is constant. So this is a dn, a small elemental radius dn, and this is the energy E, and E to E plus dE, E plus dE. So the difference between these two energies, d, small d, like that. Now, so we have represented the Fermi sphere in three-dimensional space, nx, ny, and nz. We know that all these nx, ny, and z are a different positive integer values, so that n you can consider 1 2 3 so on. For the different positive, you can take any value of n x and y and z. The energy of this, or energy of this first octant is 0. So if we have the consider the sphere, so you can divide the sphere in 1 over 8. We have to consider the 1 by 8, the octant of the sphere. So uh, then the number of available states in the sphere of radius, in the sphere of radius n is given by 1 over 8. That is 1 over 8 factor is the, we have considered the octant of the sphere and the volume of the sphere. The volume of the sphere is definitely 4 by 3 pi r cube. R is the radius, so that here it is n cube. So this is the one thing. And the second is the number of available energy states in the sphere of radius n plus dn is given by 1 over 8 4 by 3 pi n plus dn cube. So then the interval, so that is we are calculating the available energy state, that is z of e. The z of e which is into dE, which is equal to the interval between 1 over 8 4 by 3 pi n plus dn whole cube minus 1 over 8 4 by 3 n cube pi n cube. So take out the constant here, 1 over 8 4 by 3 pi, you can take constant, n plus dn whole cube minus n cube, then which is equal to 4 ones 4 twos, it is simply pi by 6. This is a plus b whole cube formula. That is, we know that a cube plus b cube, all right, I'll write the straightforward substitution, a cube plus b cube plus 3ab into a plus b. So 3ab n into dn into a plus b. So that is 3n square dn plus 3 plus 3n into dn square. A cube plus b cube, it is of the form you can write down here, a plus b whole cube, which is equal to a cube plus b cube plus 3ab into a plus b. So it is 3a square b plus 3ab square we have written, minus you have n cube. Here you have n cube also there. So this n cube is going to be cancelled. So then pi by 6 here, dn cube plus 3n square dn plus 3n dn square is as it is. But we know that here this n is the radius, the dn is very small elemental radius. Of course this dn is small. So if dn is small, dn cube is very small, and dn square also small, so that we have to, this dn cube is goes to 0, so this is also goes to 0. As it is, we retain pi by 6 into 3n square dn, so that is equal to z of e into de, that is z of e into de. So now, so this is simply, you can write down pi by 6, pi by 3 ones are 3 twos are pi by 2 n square dn. Again further, we know that we know that that is n square is e square, e is equal to n square h square divided by 8ma square. I need here this n square, just cross multiply 8ma square e divided by h square, and it is simply, I want n which is equal to 8ma square e uh, by h square. It is 1 over 2 and to e 1 over 2. So but I straightforward consider this one, I differentiate this, it is 2n into dn, which is equal to 8ma square divided by h square. With respect to de, it is de, but I want this dn which is equal to 1 over 2n into 8ma square h square into d. Then we have the z of e into de, z of e into de, which is equal to pi by 2 n square dn. So here I split this n square into dn is n into dn. It is of the form, you can see pi by 2 n into dn. So therefore the substitution, then made the substitution z of e into de, which is equal to pi by 2 n into dn. But we know that the n value, dn value, in the previous we have taken n is equal to 8 pi 8ma square divided by h square 1 over 2 e power 1 over 2. This is, we have taken n, and dn is, which is equal to 8 pi 8m a square h square into de. So that is, sorry, here in the, you just consider the previous one, so that is the dn is 1 over 2 8ma square divided by h square de. So substitute n and dn value in this expression. So z of e into de, which is equal to pi by 2, we know that n is, keep it as it is, and this n you have to substitute, so that is n is 8 pi 8ma square divided by h square 1 over 2. dn you have the 1 over 2n into 1 over 2n 8ma square divided by h square 1 over 2 e power of into d into d. So just cancel out the here n and this n, you are going to cancel. simply it is z of e into dE, which is equal to pi by 2. You have a factor over here, 8m a square by h cross square 1 over 2, 8m a square h square 1 over 2. It is simply, you can represent 8m a square divided by h square whole power 3 by 2, because 1 over 2 here it is simply 1, it's not 1 over 2. dn is simply, it is 1, and here this E is 1 over 2. So I took this E is 1 over 2 here, because just observe here. So this N is 8 ms square h square 1 over 2, here e power 1 over 2. But Dn is does not have that. So now, so pi by 2, 8 ms square divided h square 3 by 2. And here you have one parameter 1 over 2. So that is 1 over 2 you write as it is into so e power of into dE. Or further simplification, you can write down z of e is equal to pi by, here it is 2, 2 into 2 is pi by 4. So 8m a square divided by h square. So this is 3 by 2 into e power 1 over 2 into dE. Okay. Now, so this is a straightforward relation. We have calculated all these are the constant parameter, pi by 4, 8 ma square h square 3 by 2, and this is the varying factor. As energy changes, you can give the straightforward relation, z of e is proportional to e power half. So this is equation 5. Then here we got the z of e, that is the number of available energy states. According to Pauli exclusion principle, according to Pauli exclusion principle, not more than 2 electron, more than 2 electron can occupy the same quantum state, the same quantum state. So therefore, here there is one thing. So each available state, it is the multiplicity factor is 2, because so each quantum state is occupied by plus of and minus of electron spin. So that is 2 into pi by 4 into 8 m a square divided by h square 3 by 2 e power half to d. And this is simply represent 2 1s are 2 2s are pi by 2. You just observe here, this a, you have a denominator 2, 2 gets cancelled, it is a cube. So simply 8m divided by h square. This a cube, it is a is the lattice parameter, that is the volume of the cube. It's a cube, that is the cube of the octant we have considered. So this is the cube of the octant and its volume. All these constant, or v is equal to, that is the volume, into e power of to d. And we have a straightforward graphical representation. So that is the variation of z of e with respect to energy. It shows a parabolic curve. It is like this. So this is the energy range, like this. So these are the energy levels, small element t e, and this is z of e to d. So then we got the z of e and the available energy states. So then the total density of states, n of e into dE, which is equal to, you have the Fermi factor and the density of available energy states, that is pi by 2 8 m a square divided a is not there, h square 3 by 2 into volume v and e power of into the Fermi factor f of e. But we know that the Fermi factor f of e is 1 over 1 plus exponential of e minus ef by kBt. So therefore the total density of states, which is equal to the product of the density of available energy states, that is pi by 2 8m by h square 3 by 2 into v and the e power of into this Fermi factor, that is 1 over 1 plus exponential of e minus ef by kBt into dE. So this is the total density of states. So this density of states is the product of the number of these are the occupied states, number of available occupied states, and this is the number of available energy states in the energy range E to E plus dE and the probability deciding factor. So this is the overall density of state calculations. Thank you.